Hi children, good morning. Welcome back to our session. What is our topic? Sources of energy. So in the last class, we have learned about what do you mean by the geothermal energy with a small video. Is it? Yes. So today's our topic is nuclear energy. What's our topic? Nuclear energy. Have you heard about this one? Yes. In the Second World War, we have used the bombs, atom bomb, hydrogen bomb. Is it? Yes. These are all related to this one. Let me see what do you mean by the nuclear energy. A physical reaction which involves changes in the nucleus of an atom is called nuclear reaction. So, in the nucleus of an atom means it's the very smallest particle. In that particle further if we have divided, we are having the protons, neutrons, electrons. These three we call it as the fundamental particles. What are those? In an atom, the fundamental particles are protons, neutrons and electrons. So we said that atom only is the smallest particle. Further we can divide. In that, the nucleus of an atom is called as the nuclear reaction. You can think, ma'am, it is very small, but if we have used that nuclear bomb or the nuclear reactors, how can we produce the electricity? Yeah, in that only is that. So let me see what is that. The energy released during a nuclear reaction is called as nuclear energy. In this, the enormous amount of energy will be released. So that's why we are using the nuclear power plants, nuclear reactors. That's one of the good way. If you go for the bad way, we can use the bombs and we can destroy it. So we should not do such a things. So you can remember that Hiroshima and Nagasaki in Japan, what they have used that bombs. Still now the grass is not grown there, and few of the people, those who are new generation, they are with the abnormals. So they born like the abnormals due to by using of this nuclear weapons like the atom bomb and also as well as hydrogen bomb. Now you can think that how much power is our atom. So the energy released during the nuclear reaction is called as the nuclear energy because it comes from the nucleus of an atom. So in this we are using only the neutrons, positive one protons, negative one electrons, and the neutral one is the neutrons. So by using of the neutrons bombardment, we are going to create the electricity. For this, the neutrons are very responsible. So the nuclear energy further it has two types, that is nuclear fission reaction, nuclear fusion reaction. By using of the nuclear fission reaction, we are producing the electricity, but we are not using the fusion because it is only the reactions it is going on in the sun. Why the sun is giving this much heat and light means their nuclear fusion reactions are thermonuclear. The two thermonuclear fusion reactions are going on. So that's why we are getting off this much heat and light energy. Now in our country, what are the places? Where are the places it has located this nuclear power plants? Let me see now. Okay. So here are the places. Tarapur, Maharashtra. Rana Pratap Sagar, Rajasthan. Kalpakam, Tamil Nadu. Kakrapur, Gujarat. Narora, Uttar Pradesh. Kaiga, it's in our Karnataka. So these are the places which the nuclear power plants are installed, and we are getting the electricity by using of this. And here what is the fuel we are going to use in the nuclear reactors means it's the uranium, and it is very precious, and it will releases the radioactive radiations. That much powerful radiations will be release. That radiations only we are converting into the electricity, and we are using that electricity. And due to this, hazards also are there, children. Those who are working in the nuclear reactors, they used to wear the nuclear jackets, so that dress it will be, and they have to dispose that dress because it's very powerful of the radiations will fall on our body, means our cells will get be destroyed. So they should be very careful, and if they have inhaled that, they'll get different types of bronchial diseases, and skin allergies also will get. And those who are disposing this nuclear wastes, they have to dig the pit first of all, and they have to keep it in a steel container. They have to put it in the dig, they have to close it, because if you keep it in the plastic or if you throw like that, only means that radiation's power still it will be. After that, in the oceans or the seas, they have disposed, means that aquatic animals will be died. And what we are going to use that air or water, for us also the radiations causes will be. So we have to take still some of the precautions regarding this nuclear reactors and the nuclear energy. Okay, so this is about our nuclear energy. Okay, children.
Nuclear fission and nuclear fusion. A comparison. In nuclear fission, a heavy nucleus splits into two lighter nuclei, whereas in nuclear fusion reaction, two light nuclei combine to form a heavy nucleus. High temperature is not required to initiate the nuclear fission reaction. Very high temperature, up to 4 million degrees Celsius, is required to initiate the nuclear fusion reaction. Nuclear fission is a chain reaction. Nuclear fusion is not a chain reaction. Nuclear fission is carried by bombarding the heavy nucleus with neutron. Nuclear fusion is carried by heating light nuclei at very high temperature. Bombarding of neutrons is not required. A large amount of energy is released in nuclear fission. In nuclear fusion reactions, energy released is several times greater than fission reaction. Splitting of uranium is an example of nuclear fission. Combination of hydrogen nuclei to form helium nuclei in Sun is an example of nuclear fusion. The products formed as a result of nuclear fission are radioactive and harmful. The products formed as a result of nuclear fusion are not radioactive and are not harmful.
Have you ever been in an argument about nuclear power? We have, and we found it frustrating and confusing, so let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a peaceful spin-off of the new technology, helping the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain, the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finest hour finally came in the early 1970s when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day, the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy?